So this final series of videos on the summer assignment involve the determination of empirical and molecular formulas. An empiric formula is the smallest whole number ratio of atoms and moles in a compound. So, for example, if you have water, H2O, that formula is an empiric formula. It says that for every 2 atoms of hydrogen, there is 1 atom of oxygen. This also means that if I were to have a mole of water, there would be 12 times 10 to the 23rd hydrogen atoms and 6 times 10 to the 23rd oxygen atoms. That is a ratio of 2 moles of hydrogen to 1 mole of oxygen. So it's a ratio of atoms or moles that are used interchangeably. Now, if on the other hand you have a situation like this, let's say you had peroxide. Peroxide's formula is H2O2. That's a molecular formula. It tells you the numbers and types of atoms in a single molecule. Now, this is not an empiric formula. An empiric formula gives you the smallest ratio. 2 to 2 is not a smallest ratio. You can put 2 into both those numbers, divide that in, and the empiric formula for this would be HO. So this is a molecular formula here, and this is an empiric formula over here. For water, interestingly enough, there's no way you can reduce that. So water's molecular formula and its empiric formula are exactly the same. For a substance like sugar, which you've learned a lot, sugar being C6H12O6, that is its molecular formula. You can divide, 6 goes into all 3 of those subscripts, so you can reduce that to CH2O, and that is its empiric formula. The empiric formulas can be determined by what we call gravimetric analysis. In gravimetric analysis, we measure, that's what metric means, we measure gravity's effect on a sample. Essentially, we measure mass, and by measuring mass, we can determine the empiric formula. The molecular formula and the molecular weight are determined by other means, and we'll talk about those later. However, we will use molecular weights that have been determined by other means in some of the problems that we will do in the coming days and videos. So how can we determine both the empiric and molecular formula from a compound given 2 pieces of information? Now, they won't always have the same format. In some cases they'll give you the percentages of the elements within the compound, and they'll give you the gram formula mass of the compound. In other cases, they'll just give you masses of things in the compound, like they'll say there's 12 grams of this element and 13 grams of this element. In some cases, there might be 3 elements, and they'll give you the percentages of 2 of them and leave the other one blank. The assumption being that the percentages have to add up to 100 because they're just pieces of the pie. So, for example, imagine we have a compound, a phosphorus oxide, and we do not know the empiric or the molecular formula of the compound. But through gravimetric analysis, we know that the compound is this percentage phosphorus and this percentage oxygen, and through other analyses that we get to in the later chapters, we know the gram formula mass of the compound is this, and the gram formula mass is for the molecular substance, not the empiric formula. So, how can we determine both the empiric and molecular formula? Well, the first step is to assume that we have 100 grams. And then the second step is to get the mole ratio. Now, the first time we get the mole ratio, it's not going to be a nice even whole number. So at some point, we're going to have to turn that into a whole number ratio. And that part of the process is not really chemistry in as much as it's just basic math skills. So, we have 43.64 grams of phosphorus and 56.36 grams of oxygen. And we want to know how many moles we have of each of those. So what we do is we take our given masses, these things are our given masses, and we divide them by the formula mass of the atom. Now that's important to say the word atom because we want to know how many atoms there are in the ratio in this compound, or moles of oxygen and phosphorus atoms. So we're going to divide this by 30.97 grams per mole. That is the atomic mass of phosphorus, the average atomic mass. And we're going to divide this one by 16.00 grams per mole, which is the atomic mass, or the mass of 1 mole of oxygen atoms. And when we do this, we get two numbers. We get 1.4091, and that's the moles of phosphorus per moles of oxygen. And for moles of oxygen, we get 3.5225 moles of oxygen atoms. Now that is not a whole number ratio. So we could record this as P1.409 to O 3.5225. By the way, the order of the elements is usually from lowest electronegativity to highest. We'll talk more about that later. At this point, my expectation is that you can figure out the formulas, not necessarily know the order of the elements, although oxygen is usually last. Anyway, the next step, the way we do this, is we take this and we divide by the smallest number. And that's not like chemistry, that's just how I get a whole number ratio. So we're going to divide, right? We're going to divide by, this is step 3, I guess, smallest number. In this case, the smallest number is 1.4091. So we divide both these guys by 1.4091, 1.4091, and that gives us a much nicer. We get, for every 1 mole of phosphorus, we get 2.499 mole of oxygen. Now here's where we get into, we have to make this a whole number ratio. Here's a good solid rule. If you can round the hundredths place to something nice that's workable, then you're good to go. If you have to round something in the tenths place, you have a problem here. Essentially, right now, this looks like 1 to 2.5. And so what you can decide to do is you can multiply both these numbers by 2. And when you do that, you get, for every 1 mole of phosphorus, you get 4.98 moles of oxygen. Now that's pretty close to a whole number right there. If this had been a 4.8 something, you would be in a problematic territory. But if you can use something in the hundredths place to round, okay, to a whole number, you're probably good. So you can pretty much assume the empiric formula here is P2, sorry, that's a 2 over there, O5. That's a good empiric formula. But that's not a molecular formula. We don't know if this was a reduced formula or not. And the way we can determine that is we can figure out what the total mass of this is and compare it to the number on the other side. So if we add up our 2 P's, which each weigh 30.97 grams per mole, okay, and our 5 oxygens at 16.00 grams per mole, and we add them and we figure out what those are, it's like, let's see, 61, it's like 80.0, I think, and this comes out to 61.97, probably when I round it, and that adds up to 141.97. This number here does not match this number here. However, if we take this number and divide it into that number, we can figure out how the original molecular formula would be reduced to give us an empiric formula. And when we divide that through, we get the number 2. And what this tells us is that the empirical formula is essentially 1/2 of the molecular formula. So if we multiply both subscripts by 2, we'll get the proper molecular formula. So the molecular formula here would be P4O10. And obviously that would have a molecular weight of 283.94. It would have an empiric formula of P2O5. So basically it hits all the bells and whistles, right? Reduced, it's this thing right here, and the mass is actually equal to 283.94. So that's how you figure out the empirical and molecular formula. Critical thing here, they don't have to give you percentages. They can give you masses straight up. They don't have to give you all the percentages, but we know the percentages always add up to 100, and rounding is important. If you get something like this, if you get 1.33 like that, you cannot round that down to 1. The only time you can round basically is when you're in this hundredths place here. Oh, one last thing. You will note I did not round for sig figs really until the end. You don't want to round along the way. You want to keep 4 or 5 places after the decimal. If you start rounding early on, it will mess everything up.